Yes.
Could you give us some information about how you do the major?
You will sit down in the room.
Okay.
And I will give you the exam paper.
Okay, that's a good start.
You will start.
Okay.
You will finish.
Okay.
Then I'll give you another exam paper.
This is what I guess. So we have two parts in the exam.
Yes.
Will you give extra further details about that? Or?
For the first one, there will be no formula sheet. For the second one, there will be a comprehensive formula sheet containing all the formulas and everything. You are supposed to apply and interpret in the second one.
By Excel.
By Excel.
And for the first part?
For the first part, you will be supposed to prove mathematically.
So it's all proofs, no?
All proofs. No numerical in the first one. And in the whole exam, no numerical using the calculator.
It's computer.
It's all either by hand or by computer. No calculator.
Is there a thing by and the first part that needs computing?
No.
All the computations are in the Excel.
Yes. Between 1 and 100. In the course, we talk about interval estimate that is more important than the point estimate. So I'm giving you an interval estimate.
What's the confidence interval for the minimum?
100% confident it will be between 1 and 100. All right, gentlemen, I want you to turn off your mobiles and look at the screen for your full name. We are way behind the schedule. I'm deliberately behind the schedule. I'm deliberately going slow. Yes, I'm going slow. By this time, we should have been done with chapter 3. But it's okay. At some point, I will pick the pace. But at that point, I will be comfortable when you are comfortable. Look at the screen for your full name. Ahmad, Bender Sultan, Muhammad Mustafa, Muhammad Ahmad, Hussein Jafar, Saud Fahad. Ahmad Ahmad, you're here. Hussein Jafar, Saud Fahad, Abdullah Suleiman, Saud Abdulaziz, yes. Salman Fahad, Salman Fahad, yes. Muhammad Ahmad, Salman Abdullah, yes. Faisal Fahad, yes. Muhammad Abdullah, Fahad Khalid, Abdurrahman Adil, yes. Muhammad Suleiman, yes. Muhammad Ahmad, yes. Hamid, yes. Haytham, Adi Farooq, yes. Ibrahim Hussein, yes. Yusuf, yes. Hussein Abdul, yes. Hassan Ahmed, yes. Abdul Hadi, yes. Ahmad, Jawad, yes. Ahmad Mirza, yes. Abdul Aziz, yes. Ahmad Assam, Mishal, yes. Saad Ahmad, Fahad Saeed, yes. Abdul Aziz Abdurrahman, yes. Those who came during the attendance. Serial number? Last one? Yes, yes. Anyone who's marked absent, but he came during the attendance? Okay, by the end of the last class, I was talking about this important assignment. And let me give you more details about this assignment. It's very simple. What you have to do is, I'll give you example. You have to open Google Chrome and you have to go to this website. This website contains a number of data sets here, but you have to go to section LR1A. These data sets are specifically designed for linear regression, right? So what you have to do is you have to a very interesting first example where the math scores are dependent upon the drug concentration in your blood. Look at the description of the data. Number one, identify what is X, what is Y. It may be one-sided, it may be two-sided, right? So like in this example, the math scores are affected by the drug concentration. The other way is not true. If you start getting bad score in the math, it doesn't mean your drug concentration will start to increase. No. So you have to define what are the variables. Theoretically, tell us what is X, what is Y, how they are related. This is number one. Yes. The amount of drug in the blood, any drug, I don't know which drug. You read, you will get to know it. And then you open the data. When you open the data, you will have two columns, X and Y. In some cases, more than two columns where Y is dependent upon more X's. In that case, you can choose any predictor, any X as a predictor. Ignore the others, they will go to the error. And choose the best predictor that is available. So from here, copy the data and take it to the Excel and do this. That's it. Only one data. Yeah, for one student, just one data. Any data you're comfortable with. Only one, yes, because we haven't discussed the multiple regression so far. So for now, you will discuss only simple. You'll discuss only simple, but this section is not restricted to simple. This is linear regression. It means there will be some data sets with more than one predictors. Let me check. I think they're all, yeah, there are some data sets where there are more predictors. You can choose any predictor. Good predictor or bad predictor that will come later when you are interpreting. So it doesn't mean if your predictor is bad, you will get bad score. No, if you are able to identify that the predictor is bad, khalas, you are done with your job. So your job is not to find a good predictor, is to identify whether it's a good regression or a bad regression. Whatever you observe, report it. That's it. So I will formally write down the steps and post it on the Blackboard. And I will give you the time up to first major exam, 1 day before the first major exam. And when are we having the first major exam? 15th is unanimous decision. Unanimous?
No, so we can't say.
No, all of you agree. That means no one disagreed, right?
Yes, no one disagreed.
So let me start a poll on the Blackboard. If anyone says no, it will be 13th of October, Thursday. If anyone says no, it will be 13th of October, 6 p.m. Even one. If you don't agree among yourselves, it will be 13th of October, 6 p.m. Yes. No, it's not about the majority. It's either all of you or me. No, not in front of everyone. It will be a blind, single blinded poll. Let us, gentlemen, after the class, let us review this chapter and get done with the latest and the latest topic that we discussed, which was correlation. And we will apply today the correlation concept on Excel, and I will complete the interval estimate also for the correlation. Now, in the last class, I told you that there is an approximation which says that tangent hyperbolic inverse of correlation, sample correlation, follows a normal distribution, approximate normal distribution. Let me write it. And this approximation is good when n goes to infinity. That means the bigger the n, the better the approximation. So this follows approximate normal distribution with the mean tangent hyperbolic inverse of population correlation, and the variance is the inverse of n-3. So we can use this approximation also to derive a confidence interval for rho. So if one is interested in the confidence interval for rho, you can use this z. You can use this z. and I'll tell you how. Now, what we did in the last class, we defined this Z to be tangent hyperbolic inverse of sample correlation minus tangent hyperbolic inverse of population correlation over square root of the variance, right? Now, tell me, if I have a normal standard normal distribution with zero mean between plus infinity and minus infinity, if I want the 2 points such that the in-between area is 95%, what are those 2 points? And these are minus 1.96 and 1.96. Anyone who has any confusion about this one, the in-between area is 0.95. Is this clear to you?
Yes.
What if I want to make it 90%? You'll get different values. You'll get smaller values than 1.96, right? The area will shrink inside, and the values of the corresponding values of Z will be smaller, right? What if I need 99%? You have to expand, and the values will be 2.33 and minus 2.33. Yes. Now, what if I want in general 1 minus alpha? The general notation, let's call, instead of 0.95, 0.99, 0.90, what if I say I want in general 1 minus alpha to be inside? What is the remaining? Alpha, right? You have to distribute half of it to the right side, half of it to the. So in general, these 2 points will be minus Z alpha by 2 and Z alpha by 2. Clear? In general, if I want the in-between area to be 1 minus alpha, outside will be alpha. So it's just a notation. These 2 points will be. So notationally, the probability of Z between these 2 points is 1 minus alpha, correct? Correct?
Yes.
Any confusion until this point? Now this Z is basically the variable, true? This Z can be obtained from whatever objective you have. If you are trying to estimate the mean, this Z will be X bar minus mu over sigma over square root of N. If you're trying to estimate the double mean, it will be X1 bar minus X2 bar minus mu1 minus mu2 over. It depends upon what is your objective. Here in our objective, we are trying to estimate the correlation, right? So this Z will be this Z. Right? So if I put this Z in here, it will be N minus 3 square root times tangent hyperbolic inverse of R minus tangent hyperbolic inverse of rho to stay between Z alpha by 2 minus and Z alpha by 2 plus. This probability is 1 minus alpha. Any confusion? Again? Can be equal? It's Z is continuous, so it doesn't matter. For continuous, it doesn't matter if you put equal or not. Any confusion? Now, what I want you to do is I want you to manipulate this equation inside. Sorry. This whole equation inside such that ultimately you have only rho in between. And that will be a confidence interval for rho. The probability of rho between this and this is 1 minus alpha. This is what we are interested in. I want these two. This will be the lower confidence limit. This will be the upper confidence limit. What do I want? I want only rho in the middle. So I'll do small operations here and there. I'll divide both sides by the square root of n minus 3. N minus 3 I'll get rid of. Then I will subtract tangent hyperbolic inverse of r. I'll get rid of tangent hyperbolic inverse r from the middle. Then there is a negative sign. I will multiply with negative throughout. I will get rid of the negative. Then there is tangent hyperbolic inverse. I will operate tangent hyperbolic on all the sides, I will get tangent hyperbolic, I will get rid, and ultimately I will have rho in the middle, right? That will be my final confidence interval. So let us do that. Yes.
Z in the middle, you got from the previous formula.
Again?
That Z that you substituted with the whole thing is the
Yes.
previous formula.
Yeah, it can be anything according to your objective. This Z can be x bar minus mu over sigma over square root of n.
For this case, it's
Yeah, it's what you are trying to derive. If you are trying to derive a confidence interval for mu, this will be Z. If you want it for rho, this will be Z. Again?
That is the statistic.
The test statistic. If you want me to tell you the exact terminology, we call it pivotal quantity. Let's not go into that. Alas. 302, you will get to know what is pivotal quantity. You already took it?
Yes.
My feelings with you. First thing I'll do is I'll divide all the three sides by the square root of n minus 3. To get rid. So I will have only tangent hyperbolic inverse of r minus tangent hyperbolic inverse of rho z alpha by 2 over square root of n minus 3 and 1 minus alpha over square root of n minus 3. Correct? Anyone who says this is not correct? Yes, Abdulaziz. Why did I divide it on the right side? Because I have to balance the equality. No? Anyone else who has a problem with this expression? What's the problem? I should not? Why I should not?
Because it has the same value.
It has the same value.
Yes, I'm dividing inside the probability brackets. This is the same value as 1 minus 7. So I'm just manipulating the expression.
The final step.
The inequality I am manipulating with is basically in this expression, the expression above, there are two equations, not one equation. I'm talking about one equation is probability of something equals 1 minus alpha. This is one equation. I'm not manipulating with this example. I'm not playing around with this equation. There is another equation inside the question mark. It's a three-sided inequality. Inside the question mark, there is another equation. I'm only manipulating with that equation. So I'll stick to that equation. Any operation will not come out of the bracket because I'm only playing around within the brackets. It's a complete inequality within the bracket. So the thing that I did will stay inside the bracket. One inequality is this inequality in this black circle. The second inequality, the second one is inequality. And equality is the whole thing. Probability of something equals 1 minus alpha. This is something. If I want to play around with the overall inequality, I should do this. Whole divided by n minus 3, whole divided by n minus 3, which I'm not interested in. So I'll not do that. I'm only interested in within the brackets. Within the brackets, I want rho in the middle. So this is the correct way of doing it. And then tangent hyperbolic inverse of r, I'll subtract throughout from all the three sides. So I will have probability minus z alpha by 2 over n minus 3 square root minus tangent hyperbolic inverse of r less than minus tangent hyperbolic inverse of rho less than z alpha by 2 over square root of n minus 3 minus tangent hyperbolic inverse of r to be 1 minus. So I subtracted tangent hyperbolic inverse of r throughout. Next, get rid of the minus. But when you get rid of the minus, what will happen to the inequality? They will reverse. So when you multiply it by minus, the greater will become less, less will become greater. So this will happen. this will happen. I multiplied this with minus and it's here. This with minus and it's here. Clear? Now what? Apply the tangent hyperbolic on both all the three sides and you will be done. So you have probability tangent hyperbolic of tangent hyperbolic inverse r plus z alpha by 2 over n minus 3 square root. So greater than rho greater than tangent hyperbolic of tangent hyperbolic inverse of r minus z alpha by 2 over n minus 3 equals 1 minus alpha. And we are done. Now, because the inequality is left-sided, I'll write the same thing in the other way. So that will be probability. I'll write this one here. The lower limit, I will write it first. Tangent hyperbolic, which minus? I forgot.
The right side. N minus 3 and the square. You get it from. And then the square root in the right side.
This one?
Yes.
What did I do?
N minus 3.
Minus? Tangent hyperbolic of tangent hyperbolic inverse of r minus z alpha by 2 over n minus 3 rho and this is equal to 1 minus alpha, and we are done. This is called the lower confidence limit. And this is called the. Now you can put any value of alpha you like. If alpha is the 0.05, you will get a 95% confidence interval. And the corresponding values of z will be 1.96 and yeah. What is the meaning of tangent hyperbolic? What is the meaning of tangent hyperbolic? We don't need to know this. But if you need to know this, which course have you taken? 101, 102 or 105, 106? You can find the answer there. It will be there. Yeah, to cancel the effect. Yeah, it's like sine and sine inverse, cosine, cosine inverse. It's the same effect. If you want. We didn't study. I cannot believe. I'm not talking about 105, 106 now. Now I'm talking about 001 and 002. You don't take 001, 002? If you want me to go, I'll go to the high school now.
So they will go.
Yeah. If you want to cancel the tangent hyperbolic inverse, you apply tangent hyperbolic. If you want to cancel tangent hyperbolic, you apply the inverse. Exactly like sine, you want to cancel, apply the sine inverse, and so on. So the final confidence interval, it is like this. It is tangent hyperbolic of tangent hyperbolic inverse of r plus minus z alpha by 2 over square root of n minus 3. And I think this is the expression that you will have, the final expression in your book. Now what we are going to do is we are going to apply this on the same rocket propellant data, where first we will find the correlation and then we will try to Then we will try to construct a 1 minus alpha % confidence interval. It's here. Tangent hyperbolic inverse of r plus minus z alpha by 2 over square root of n minus 3. The same, we got it. They are applying it on delivery time data. What data we have? Propellant. Is this a different data? Let's 25 observations. Let me see if I have this data. If I have it, we'll apply so that rocket propellant delivery time, we have it. So let me apply this on delivery time data, and so that we can compare the results. Copy this file. In the meantime, let us read the description of the variables. Consider the soft drink data introduced in chapter 1. It was introduced in chapter 1. The 25 observations on delivery time and delivery volume. What is it? Table 2.11. It's the delivery time, maybe the time for filling the vending machine, and the delivery volume, the number of items you have to fill. I think it is that. If you are confused, you can go and read the description of what is Y and what is X. I think it is that. So here is the data. We have 25 observations on delivery time and 25 observation on the delivery volume, represented by the number of cases. So what we need to do is, the first thing we need to do is we need a point estimate of the correlation, and the point estimate of the correlation is R, where R is where? It's here. SXY over SXX times SSY whole square root. So I need these three quantities, and for these three quantities, I need the 5 basic columns: column of X, column of Y, column of XY, column of X square, column of Y square. 5 basic columns. 2 I already have, so I'll create the remaining 3. XY, X square, Y square. XY will be this value multiplied by this value. X square will be simply this square. And Y square will be simply Y square. Once I have the sums of all 5 columns, which is what I need, I can calculate. First column is Y. SXY, SXX, and SYY. For SXY, it is summation of XY, this one, minus summation X times summation Y over, I chose a different one, summation Y over N. Do I have N? No. Let me save this as N. Yeah. So I saved N as 25. I got SXX, XXY, sorry. SXX will be summation X square minus summation X whole square over N. Okay. I don't think I need bracket for multiplication division. Okay. If I put a square, then I need a bracket. Summation Y square minus summation Y over N. So here I have SXY, SXX, and all that. So now I'll calculate R. I'm not going towards the regression now. I'm going towards correlation now. R will be SXY over square root of this multiplied by this. What I expect is, I expect it to be 0.9694. 0.9646. 0.9646. So I get the exact same answer as the book. So how do you interpret this value? Strong positive linear association between y and x. You will not say y and x, you will name the variables between the delivery time and delivery volume. Because it's close to +1. Even if it's close to -1, you will say strong negative, still strong. Now let us say you want to create a 90% confidence interval. So your alpha is 10%. Your z alpha by 2 will be what? One minus this alpha by 2 will be the lower tail area. And I don't think you need degree of freedom for z. Carefully look at what I put inside. Norms inverse means that I want a value of z corresponding to this probability. You will use the inverse when you're using the inverse use of the table. You remember the table, we use it two ways. The direct use of the table gives you the probability against a value. The inverse use of the table gives you the value against a probability. So you're using the table inversely. Again, yeah, you need the value against this probability. And what is the probability? To understand the probability, go back to this diagram. This diagram. For this diagram, you need that upper z alpha by 2. Now, what is the lower area? The lower area is 1 minus alpha plus this other alpha by 2. So the overall lower tail area is basically 1 minus alpha by 2. That's why I put 1 minus alpha by 2. So this will give you 1.645 for 90%. If you make it 0.05, this will give you the most popular 1.96 that we use. Right? So once we have this one, I can directly go and find the lower limit, which is tangent hyperbolic. Now this is a long formula. Tangent hyperbolic equals tangent hyperbolic. This is the command, tangent hyperbolic of what? Inverse tangent hyperbolic, a tangent hyperbolic of this r. Then minus this z alpha by 2 over square root of n minus 3. 0.92 is the lower limit. And I copy this whole thing with a plus sign. That will be my upper limit. .98 is the upper limit. So I will say I am 95% confident that the correlation between y and x is between 0.92 and 0.9845. According to the value of alpha, you will interpret it. What if I increase alpha? What will happen to the interval? Widen or it will shrink? If I increase alpha, it will shrink. If I increase alpha, outside area will increase, inside will decrease, so the values will get closer to 0. So if I increase, for example, to 0.1, the interval will shrink. If I make it 0.5, the interval will shrink, 0.95 to 0.7. And if I decrease the value of alpha, I need to be more confident. When I want to be more confident, I need to give bigger limits. So let's say if I want to be 0.001, it will be wider limits. So I can say I'm 99.9% confident that the rho is between 0.86 and 0.99. Any questions? No questions? Now, what I want you to do is after this class, I want you to go to the blackboard. Regardless whether you have taken matrices or you haven't taken matrices, I have found a very comprehensive review of only basic matrix terminologies which are used in regression. No extra terminology. So I have posted that thing on the blackboard. in which it's explained what is a matrix, what is matrix addition, what is matrix subtraction, what is matrix multiplication, what is inverse of a matrix, what is the rank of a matrix, only the concerned things that we will use in this course. And the file is called, what is it called? It's called Introduction to Matrices. When you open this file, I want you to go through this file. This is a 21 pages file during the weekend. When you come back on Sunday, I don't want to see an excuse that I don't know what is the addition of matrix. What is the definition of matrix? So when you go back, you will see first the definition of a matrix. What is a matrix? Then very easily they will explain the square of the matrix. They will explain the square matrix, which I don't know. They will explain it. They will explain the vector, which is a special case of matrix with one column. They will explain the transpose of a matrix. They will explain the equality of matrices. They will explain the addition and subtraction. It's very easy. They will explain the multiplication of matrix with a scalar quantity, a single quantity. They will explain the multiplication of matrix with a matrix. When is it possible to multiply and how to multiply? They will explain all of it. They will explain. We will not take any of this, but we'll use all of it. We'll use all of it. We'll talk about what is a symmetric matrix, what is a diagonal matrix. These are all very frequently used in regression. We'll talk about what is an identity matrix. Yes. This is chapter 3 and onwards. And onwards. And finally, you'll talk about the rank of the matrix. And the rank of the matrix will tell you how many linear dependencies are there inside the matrix. So during the weekend, I want you to go through this one. Don't go towards manually how to find the inverse, because Excel will do it for you. Don't go towards manually finding the rank of the matrix. Excel will do it for you. Don't go manually towards addition of the matrix. Excel will do it for you. Just get to know what is addition, how it is done, what is subtraction, how it is done. Don't care about how they are doing it. They will give you the practical examples of inverse of a matrix. You don't need to. You don't need to do. Look here. I enter a matrix 1, 2, 3, 4. And I want the inverse of this one. What I'll do is I'll select a 2 by 2 space. I'll write M inverse. And I'll select this matrix. This will give me what happened. It's not, the Excel version is changed. M inverse, it's complete inverse. The one I used to use. This will give you the inverse of the matrix in one command. You don't need to care for how to find it manually. Excel will do it for you. So don't worry about the manual procedure. You need to understand what is inverse. That's it. I have a better thing to do for now. Chapter 3. No, for this weekend, the 2 I gave you are more than enough. Now, since the start of chapter 2, we have been assuming that y is dependent upon only one variable. Is it true in the real life? It's not. Usually your response variable is dependent upon many variables. Some of them are seriously affecting it. Some of them are not seriously affecting it. Right? So if you look at the predictors, all the predictors which are seriously affecting y, it can be more than one. True? So in that case, we should not stick to the simple linear regression. We should extend it to the multiple linear regression, where the model is something like this. So you see, I extended this part. I extended that part where there was only one predictor. Now I have k predictors. Clear? How will the data look like? I'll explain it to you. The data will look like this. You will have a column of yi, where you will have y1, y2, y3, all the way up to yn. You need to understand the difference between n and k. N is the number of units on which your data is available. Suppose y is the score of the student. So this y1 is the score of the first student. Y2 is the score of the second student. Y3 is the score of the third student, and so on. Yn is the score of the last student in my sample. Sample size. And then x's are the variables that are affecting y. Suppose x1 is the study time. So I will have x1 1, x1 2, x1 3, all the way up to xn 1n. Study time of the first student, study time of the second student, study time of the third student, and so on. Let's say x2 is the number of other courses student is taking. More courses means more load, so it will inversely affect the score of this course. So that's the assumption. So it'll be x2 1, x2 2, 2 3, and so on, x2n. And suppose I have the last predictor, which is xk. So it'll be xk1, xk2, xk3, all the way up to xkn. Now there is a binding factor between these values. What is the binding factor? Between y1, x11, x21, xk1, there is a binding factor. What is the binding factor? Behind all these observations, there is a single student, student number 1. These all are for that student. Y1 is the score of that student. X11 is the study time of that same student. X21 is the number of other courses for that same. So for each row, there is a binding factor. That binding factor is I, student number. So there is something called I and there is something called J. I will use it for the student number or the observation number. J, I will use it for the predictor number. Predictor number. No K. I equals K, I'll take it as a constant. K is the number of predictors. I varies from 1 to all the way up to n. J varies from 1 to all the way up to K. When J is 1, I'm talking about the first predictor. When J is 2, I'm talking about X2. When J is 3, I'm talking about X3, and so on. This one is the J and this one is the I. Yeah. So this whole data is written in this equation. Yi equals beta naught plus beta 1 x 1I plus beta 2 x 2I plus all the way up to beta k x ki plus epsilon I. You understand it? Where I is 1, 2, all the way up to n. Clear? This whole table, I wrote it into a single regression model. Yi's are y's.
Yes, but there are different Ys for the same X, so I don't know how they are different.
From student to student, from observation to observation, y is changing.
Okay, and we plug that into the model.
Shouldn't be J because we're talking about the.
If you want to write it in a more compact form, I can write it this way. Yi equals beta naught plus beta j summation of beta j x ji plus epsilon I, where j equals 1 to k. This is even more compact form of the same thing. But I'll not use this one very frequently. Summation because this is the sum of these things. I wrote whole this thing into a single summation. But I'll be rarely using this notation. More frequently, I'll be using this notation. Now, this regression model is what we are going to deal with in chapter 3. But what I'm going to do is I'm going to define a matrix notation for this same model. And in that, what I will do is look carefully. And remember, this is my objective in the circle. I have to get to this equation. I need to write this thing in terms of matrices. What I do is I define y as a vector in which I have y1, I have y2, all the way up to yn. So y is this column, this column. Clear? Then I define X to be as a matrix, and this will be X11, X12, 1, 2, or 1, 1, 1, 2. Now this is happening to me since I upgraded to Windows 11, and I have no idea. What should I do now? I'm back. This is the first variable, and then x21, x22, all the way up to x2n, xk1, xk2, all the way up to xkn. This is my X matrix. Then I define beta as a vector. There will be beta 1 naught, beta 1, beta 2, all the way up to beta. And finally, I define epsilon as a vector. And this will be epsilon 1, epsilon 2, all the way up to epsilon n. Now, I want you to go and check if I write y vector equals x beta plus epsilon. Do you get this model back? Go and check. And the answer is you will not get it back. Why? Because when you will miss B naught. There is no B naught. There is no margin for this. This is, you cannot multiply these two. The multiplication is not possible. Because the number of columns of beta is k plus 1, and the number of rows of this one, the number of rows of this one is k plus 1, and the number of columns of x is k, not k plus 1. So the multiplication is not possible. To make it possible and to compensate for the intercept, add another column of ones at the start. Now, when you multiply these two and then finally add it to the epsilon, you will see you will get this same table back. I want you to go and see that this will give you that table. Exactly that table, where the order of y is n cross 1. How many rows? N rows. How many columns? 1 column. The order of x is what? How many rows? N. Same n rows. How many columns? K plus 1. A column of ones at the start. An extra column to compensate beta naught. How many rows of beta? K plus 1. How many columns? 1 column. How many rows of epsilon? And how many columns? 1. Now look, is it possible to multiply x with beta? Look, how many columns of x and how many rows of beta? Are they equal?
Yes.
Multiplication is possible. What will be the result? N by 1. So is it possible to add n by 1 with n by 1?
Yes.
What is the result? N by 1, which is equal to n by 1. So you will get this table back. This table or this model, you will get it back. So what we did is we did nothing new. We just denoted the same model into a matrix notation. That's it. We are doing that because in this model, now this is the unknown parameter. We'll try to estimate it. Because this beta contains all the betas. If you have any questions, you can stay. Otherwise, I will see you on Sunday, inshallah. Now I will create the poll on Blackboard now. And if I see any no, immediately I will announce the date and time of the exam, which will be Thursday, 6 p.m. Thursday, 6 p.m.
Can you make the deadline today so we can know our schedule
Deadline for what?
for the pool? So
Yeah.
we all should respond before midnight.
Let me do it now.
I don't know that someone disagreed that we are going to make the exam earlier.
No, not earlier. It will be Thursday, 13th.
For the betas, shouldn't we take the transport and get that?
No. Go and try and multiply and see. You will see it. You don't need transpose or anything.
It's not a column vector.
Again?
Betas here, it's not a column vector, it's a row vector.
No, it's a column vector. It's a column vector. Give me 6 p.m. 6 p.m. I'm preferring because it's immediately after Maghrib prayers. And you don't need a break for the prayers after that one. Isha, you can pray a little bit late also.
Yeah, number 2.
Number 2. Number 6.
Also, Doctor, last class you marked me as absent.
Yes. So I should not mark you absent.
14.
Number 1, 4.
Thank you.
That's it?
Excellent. Question.
Yes.
Here, for the covariance, could we make it like this, variance of xi?
No, not directly. The concept is correct, but not directly. Let me explain it to you.